Good morning, everyone. Welcome, and thank you for joining us again on Facebook Live. We're excited to have you back this morning. I'm Amber, the Public Science Events Manager at the Bell Museum, and today, or this morning, I'm actually joined by one of our planetarium education staff, Caitlin, who is going to continue us on our journey through the solar system. So this is the second part of what she started in terms of talking about all of the wonderful things in our solar system. And as we're going through this today, as always on Facebook Live, we'll be watching the comments for your questions. So please feel free to type them all in there so that Caitlin and our planetarium staff can answer them once the presentation is done. We'll be watching them closely and we'll get to as many as we possibly can. So thank you again for joining us. Caitlin, I'm going to turn it over to you.
Thank you very much, Amber. Hi, everyone. It's good to, well, I suppose I can't see you, but you can all see me. It is good to see you all again. Now, today, we're going to be taking a look at something that we see every single day. We're going to be looking at the sun. And if we have time, we might just leave our solar system behind and go take a look at a few other stars. But without any further ado, we are going to go ahead and get started today. All right. So we've got this wonderful black screen up, but that's a little boring. That's not anything interesting to look at. So let's take that down, and we are floating above our solar system. But instead of visiting any of the planets, we're going to head straight in to that big, bright star that's right at the center of our solar system. And we're going to be able to take a look at it that, well, most people don't ever get to see unless you've somehow managed to get on a very advanced spacecraft going close to the sun, because we're going to go see the surface of the sun today. Now, let's see. The surface of the sun shouldn't be just completely white, so we're going to head out a little bit and just make sure that it's on. It wasn't on. All right, we fixed the sun. Let's head back in. Now, the sun is a star just like any other star that we see in our sky. In fact, it's a pretty average star and pretty calm. But when you get up close, it looks a lot different than it does in our sky. And I'm talking about looking at the sun in our sky. I want you to remember that if you're going to look at the sun in the sky, you have to have special protective glasses so that you don't go blind. But even if you do look at it with those protective glasses, you probably won't see what we're seeing here on the sun. So we're going to get a little laser pointer on. And right over here, we have a little dark spot. Now, a sunspot is the region that's slightly cooler and has a much stronger magnetic field. It's like the magnets that are on your fridge, except think of it as a spot on the sun that could maybe stick to your fridge. Although the sun's a lot bigger than your fridges at home. And do you notice on the sun here all of these different swirls? Those swirls, and we'll get a little bit closer to see them, are what we call convection cells. So those are areas where the sun is taking stuff from deep inside and bringing it to the surface, and the stuff on the surface is going back deep inside the sun. Because the sun actually has three main parts to it. And to get a look at those three main areas, we're actually going to go take a look at a model of the sun that's, well, a little bit further away from our solar system because we didn't want to stick a second sun right into our solar system. So we're going to spin around so that we're pointing at it, and then hold on tight because we're heading a little further out. So you can see the glow of the Milky Way galaxy there in the background. We're headed towards the center of it, though we won't get all the way to the center. And we don't want to. There's a giant black hole there. And here is our model sun. So you can see it has kind of that same patterning on it, where you see all the little convection cells. But the reason we came to this one was because this model sun lets us do something that the sun we were at before doesn't. We can go ahead and cut this sun in half. And if we move around, we can see the layers of it. Now, inside the sun, we have 3 main layers. We have the core, and this is where something called fusion happens. This is where the sun makes all of its energy. And that energy goes out through these other 2 zones. And these other 2 zones, we have the radiation zone and the convection zone, like those convection cells that we talked about. And then you also have the sun's atmosphere. Now, the sun's atmosphere isn't much like the one we have here on Earth. Well, it's a lot hotter. It can get to be millions of degrees Fahrenheit in the sun's atmosphere. But it has the photosphere, this part really close to the sun, and that's what we see from here on Earth. It also has the chromosphere, or where the solar corona is. And this section is what you'll see during a total eclipse, kind of that halo around the sun and the moon. Now, right now we have these 3 different colors, a darker pink, a lighter pink, and a white. But in reality, those are probably all pretty similar colors and not pink. To us, they would likely look kind of a yellowish orange. Now, let's see. We could head back to the solar system and talk a little bit about why we're looking at the sun today. Or we could patch this star up and head out to another star. What do you want to do? Yeah, I think we should go to another star. The sun can be a little bit boring, and we've got so many other stars to take a look at. All right, so we patched that one up. And we're now going to spin around to point ourselves at a star named, well, there's multiple ways to pronounce the name. Most people I know call it Betelgeuse. You can also call it Betelgeuse if you want to maybe pronounce it a bit better. But this is a star that's in the constellation Orion, one that we can't see anymore. And it's a red giant. Now, if it's a red giant, what color do you think it's going to look like when we get there? Well, we will find out in just a moment. It is a dark reddish orange. This looks a lot different than the stars we were at. And we can see it looks a little bit puffier on the edges. If we look over here, it looks like it has more, well, puffiness. That's because it is a star that's puffing out more. It's a red giant. It's at the end of its lifespan. So it's puffing outwards and getting bigger and getting less dense. So the stuff that makes it up is spread out more. And that makes it look very red in our sky. In fact, in our sky right now, there are a few stars you can find that are pretty bright and very red. One of them is a star called Antares that's pretty similar to Betelgeuse, but it's in the constellation of Scorpius, and it's pretty often confused for the planet Mars because it looks red in our sky. But you've seen this star here, and you know that stars can be red. So if you go look for that tonight, make sure you don't get tricked. But if you do, don't worry. Antares just translates into not Mars, so you aren't the first person to get tricked. Now, let's head back towards our solar system, because we're getting kind of close to our time limit here, and I don't think any of you want to be left floating outside the solar system, as pretty as all these stars might be. So we're going to head back home, back to our sun, and talk about why we chose to focus on stars today. And why we didn't for our very first show, because the star, the sun, is where we get all of our light and energy. It's what makes life possible. It would make sense to start with the sun as our very first thing for our Out of This World series. And the reason we didn't is because we knew that we had this special day coming up pretty soon that would be perfect for looking at the sun. And that day was this past Saturday, the summer solstice. Now, the summer solstice here in the northern hemisphere is the time when the sun is in our sky for the longest. So if you notice that Saturday felt like it was daylight for a really long time, you're right. It was the longest day of the year for us. But it was also the shortest day of the year for people in the southern hemisphere. For them, it's their winter solstice. And the reason that is because the Earth is slightly tilted. And as we go around the sun, sometimes the northern hemisphere is pointed towards the sun, and sometimes it's pointed away, and same for the southern hemisphere. In fact, if we go take a look at the Earth, we might just be able to see that. So we're passing by that red line, that orbit of our moon, and here we have our Earth. In fact, if you look right over here, this is about where Minnesota would be. But to get an idea of how the Earth is tilted, we need to do one more thing. And what that is that we need to show you exactly where the kind of line, the poles for the Earth are. And so if we go ahead and see if we can turn those on, they might not work today. And if not, well, then I might just pop on my video and we'll take a look at a less interesting demo. Okay, so we're going to take a look, unfortunately not at the screen anymore, but rather at my face. And hold on just a moment because I can't quite figure out how to stop sharing my screen. All right. There it is. The little red button that says stop share should usually work. I'm sorry about that, folks. So we're going to pretend here that my fist is the Earth. It's a very round Earth. And this pen between it is got the North Pole and the South Pole. And let's see, what do I have that can be the sun? Well, I have a second hand. So we have the sun, and then the Earth, and the poles. And as the Earth goes around the sun, you can see that that tilt sometimes has the northern hemisphere pointing towards the sun. But if we kept going around, it's pointing away. And over here, it would be winter. And over here, it's summer. And when we're pointing most towards the sun is when we have our summer solstice, that longest day of the year. Since we had that this past weekend, we wanted to talk about the sun with you all. Now, I've talked a lot, and I want to know now if any of you have any questions for me. Because we talked about a lot of different stuff. And I know Amber's been monitoring the chat. So Amber, do we have anything popping up yet?
Yeah, we did have a few questions that popped up. And we even had someone join us from as far away as Kentucky this morning. So,
oh my goodness, welcome.
So the first question that we had, Amy and a couple other people are asking why it is that we can't see Betelgeuse anymore.
Why can't we see Betelgeuse anymore? Well, that's because we see different constellations during different seasons. Because that same kind of tilt and movement, the revolution of the Earth around the sun, means that if we're in the nighttime over in the winter, we're looking this way at the stars. But if we're at the nighttime in the summer, we're going to be looking at stars that are over here. It's a different set of stars. Now, because of where we are, at least in Minnesota, I'm not too sure about Kentucky, But here in Minnesota, we have some stars that we see all the time because we're pointed almost directly at them. Those would be things like the stars in the Big and Little Dipper. But the stars in Orion, we don't actually see all the time. So when we don't see them, like right now, it's, well, because they're either out during the daytime when we have one star that's drowning out all of the others, and that would be our sun, or they've just dipped below the plane of what we can see, so they're being seen from the southern hemisphere.
Okay, and I have a couple more questions that have rolled in. Jesse is wondering, where do stars get their oxygen to burn?
Where do stars get their oxygen to burn? It's a good question. And it gives me a chance to talk about what stars are actually doing to make their light. Because, well, they're not actually burning like a fire. Fusion is a little bit different. Because fusion is mostly in stars happening between hydrogen and hydrogen, or hydrogen and helium. And, well, hydrogen and helium, think of the stuff that you put in balloons. That's most of what the stars are made of. And inside the very center of a star, inside that core, there's so much pressure and heat and gravity that it's taking those little bits of hydrogen and smashing them together. And when they smash together, they can bond to create a larger element. And that bond also makes energy, which is where we get the light and heat from the sun. So it actually doesn't need oxygen at all. And stars do eventually produce oxygen, because as they smash together hydrogen, they get helium, and they smash together helium and get bigger elements and keep smashing all of those together up until iron, and then they explode. But it doesn't actually burn anything. It's just fusing them, sticking them together, and that gives us all the light from the sun.
The next question actually comes from Kelly, and Kelly's wondering when there will be more sunspots.
Oh, when will there be more sunspots? That is a great question. So, our sun goes through cycles of activity, or basically napping. And we call those solar minima and solar maxima. And the sun's been in a solar minima, so it's not been very energetic. And those cycles take about 11 years to go through, so we're hoping to see more soon. But there are websites you can go to, like the Solar Dynamics Observatory, and I'm wondering if maybe we could drop that in chat, that you can go and look for sunspots to see if there's any on the sun. Now, we've been wanting to get a picture of a sunspot to share with you all. We've been wanting to get that since March, and the couple days that we saw there were sunspots, it was cloudy, so we couldn't get anything for you. So it's been really quiet recently. But hopefully in a few years, we'll be able to see a little bit more entertaining things happening.
One of our 5-year-old guests has an interesting question and just wants to know why the sun is so bright.
Why is the sun so bright? Well, mostly because it's close to us. Because all the other stars are really, really far away. And think of it as a candle. If you're standing in your house and you're holding a candle and all the lights are out and it's right in front of you, is that flame going to be bright, or is it going to be really, really dim? And then if your parent is holding a candle in the house, but they're standing all the way across the room, is your candle going to look brighter than your parents, or is it going to look darker? Well, it's probably going to be that your candle looks brighter because it's right in front of you. But if they're the same candle, they're both going to be about the same brightness. It's just that one's further away, so you don't see as much light. And if we bring that back to the sun is a star just like all of the other stars in our sky. It's just right next to us. It's only 93 million miles away, which sounds like a lot, but the others are hundreds of trillions of miles away. So it's really, really bright to us.
Can you tell us a little bit more about our sun as a star? Like, how old is it and how much longer do we expect it to live?
So the sun is about 4.5 to 5 billion years old, same age as the solar system. The sun forming is what kickstarted the solar system forming. And we think its entire lifespan will be about 10 billion years, which means that it has about 5 billion years left, which is a very long time. Now, when it dies, it's going to be a little bit boring. It's going to turn into one of those red giant stars. So as it starts to get really old in a few billion years, we don't need to worry about this yet, it's going to start to puff up like Betelgeuse did. And as it puffs up, it's going to expand all the way out, potentially to Jupiter, which means that the Earth is going to be inside the sun. But that's a few billion years away. Now, the sun's not ever going to explode. It's just going to puff up and then shrink back down.
It's good to know we've got a couple of years. Yeah. We've also had a couple of questions just in general about eclipses. Do you know, or can you tell us a little bit more about when the next eclipse event will be?
Well, there was one, I think, last night. That was an annular solar eclipse. And I say last night because it was nighttime for us. That solar eclipse happened on the other side of the world. Now, the next eclipse, solar eclipse, that's going to be visible from the US will be in 2024. I hope I'm getting that date right. I'm pretty sure I'm right on that, but we might have Amber fact check me and just put a correction in if I was incorrect. But it should be 2024, and it's going to go on a path about from Texas up towards Maine. Now, solar eclipses happen a lot less often than lunar eclipses. So a solar eclipse is where the moon goes between the sun and the earth, and a lunar eclipse is when the earth goes between the moon and the sun. And it's the shadow of those objects falling on us that creates the eclipse. Now, the earth's shadow is a lot bigger than the moon's shadow. So the moon passing through the earth's shadow happens a lot more than the earth passing through the moon's shadow. But the next lunar eclipse is actually coming up in July. Unfortunately, it's not a very dark one. The moon's just skimming the Earth's shadow, and we probably won't notice it. But we're going to put out a post about it when it happens, so keep your eyes peeled for that.
Great, thank you. The last thing that I see, and this is kind of an interesting thing to think about, Chi is asking us to think, and I'm sorry, I hope I'm saying their name correctly, is asking us to think about what our sun would actually look like from another planet.
Okay, so what would our sun look like from another planet? I'm assuming a planet outside of the solar system, because we actually know what it looks like from other planets in the solar system. We have rovers on Mars that have taken pictures of the sun in the sky and sent them to us. But from outside of our solar system, the sun, well, it depends on how far outside. If you're going to our nearest neighbor, Proxima Centauri, it's only about 4 light years away. The sun's going to be a pretty bright star, but it'd still look like a star in our sky, just one of the particular bright ones. Think of one of the stars in the Big Dipper. But if you went further away than our closest stars, say if you went out to where Betelgeuse is, you might not see the sun at all, because it turns out the sun's a bit on the small side for a star. And so it wouldn't necessarily be visible except to telescopes from other planets around other stars.
Thank you. That was an interesting thing to think about. And I think we've made it through all the questions that our audience has for us right now. Thank you, Caitlin, for continuing to take us on this journey through our own solar system. I just wanted to let everyone know that we appreciate you being here on Facebook Live, and to let you know that this digital programming is possible because of donors and sponsors, and every donation, no matter how big or small, really helps out. So if you're interested in being a donor for the Bell Museum, I've posted some information in our comments and a link. Please join us there if it's something that you're able and willing to do. So thank you once again for joining us this morning. Thank you to Caitlin. Everyone give Caitlin a round of applause from home. And
thank you.
we hope you all have a wonderful day. Have a great week.